Yes, welcome back. I'm Mr. Chai. Today I'm going to walk you through a full paper on A-level mechanics M1 paper 43. Let's get started. Let's look at the first questions of A-level mathematics mechanics component, um, paper 4. Right now, this is one of the compilations mechanics question. Right. Okay. Question 1. A block is pulled along a horizontal floor by a horizontal rod, right? You can see that from the diagram itself. Now the tension in the rod is 500 Newton and the block moves at a constant speed of 2.75. Now find the work done by the tension in 40 seconds and find the power applied by the tension itself. Right. Now let's take a look at how does this work, right? So all the forces that is acting on the block, you will have to label that in the exam itself. So it consists of the weight, the normal force. Now since the floor, let me see. Okay. Now, in this case, we have no idea whether the floor is a rough or smooth, but it does say is that it moves at a constant speed. So there is a tension of 500 newtons pulling towards the right. There must be a frictional force in order to produce a constant acceleration of 2.75 here. All right, now let me show you how does it look like. 40 seconds, it would have moved to position B, for instance. Okay. Now, how far is B then? Okay, so we are going to find that out shortly. Right. So let me show you how does it look like. Okay, so this is how it look like. It's going to move from A to B. Constant speed here. So which means acceleration is actually equal to 0 there. All right. Okay. Now 40-second duration. Okay. 40-second duration, how much work is being done? So work done, first of all, right, is given by, okay, the work done itself is given by this formula here. So work done is given by the force multiplied by its parallel displacement or distance in this case. So we need to know the distance the block has moved in this case. All right. Now the force. Okay, so work done by the tension. The force will actually refer to the tension itself. So in this case, we can actually write tension and then multiply by the displacement. The block has trouble in this case. Right? So first of all, we have to figure out how far it has already moved. Now, because it's moving at a constant speed, that would be quite direct in this case. So you can actually use, yeah, you can use the Suvet equation, for instance. In this case, is ut plus half a t squared. Right. Now we know that since it's moving at a constant speed, acceleration must be equal to 0. 0 meter per second square. Right. So from here, we will get the displacement is equal to initial velocity multiplied by the time itself, which is the constant speed in this case. Right. So distance will be given by 2.75 by the durations of time here. So 40 there, right? Let me see what do we have here. So that will be 110 meter. Okay, let me check one more time if that is 110 or not. Yeah, correct. So it is 110 there, right? So 2.75 by 40. I just want to confirm one more time in case I made a mistake here. So 2.75 by 40 there. Yep, so it's 110 there. Now once we have found this, okay, now getting the work done will be very straightforward. So therefore, work done will be given by the tension itself, which is 500, multiplied by the distance traveled. So 110 there. So that will be 5, okay, 55,000 joule. Right. So the work done will be 55,000 joule there. Now we have done the first part here. Right. And then next we need to find the power applied by the tension itself. So power is given by work done per unit time there. So we have already found the work done, which is 55,000 here, over the durations of time provided here, which is 40 seconds. So therefore, in this case, we should be able to get, let me see here. Okay, so I think it should be 13750 watts. Okay, so the unit is watts. Just let me check properly if I got it correct. Okay, so that will be that. Divided by 40 here. So 1375. 1375. Yeah, correct. 1375. I think I accidentally put another zero there. So 1375 watts here. All right. And then that complete our discussions for this question. I hope that is clear. I'm going to move on to the second question shortly. All right, let's take a look at the second question. Now, this is a pulley system. Now, particle A and B of masses 0.35 kilogram and 0.15 kilogram respectively attached to the ends of a light inextensible string, okay, as shown in the diagram. Now, A is held at a rest on a smooth horizontal surface with the string passing over a small smooth pulley fixed at the edge of the surface. Okay. Now B hangs vertically below the pulley at a distant h above the floor. A is released and the particles start to move. Now B reaches the floor and A subsequently reaches the pulley with a speed of 3 meter per second. Now the first question here, explain briefly why the speed with which B reaches the floor is 3 meter per second there, right? Okay, now let's take a look at how to explain on this. We're going to make use of all the informations given to us. Now the information given to us is here. Right, A subsequently reaches the pulley with a speed of 3 meter per second. Okay, when B reaches the floor. Okay, now there's a lot of subjectivity here. Okay, now we are going to start off by analyzing just before B touched down. Okay, now just before when when B is about to reach uh, is about to reach the floor. Okay, sorry about that. There's a delay here. When it's about to reach the floor. All right. Now when it's just about to reach the floor, now both speed of A and B is maximum. Okay, both the speed of A and B is maximum while the string is still taut. Okay, while there's still a tension, when the object just about to touch the floor, then both the speed of A and B would be maximum. Okay, and then the speed would be maximum at this point because the B is about to hit the floor. Now the moment B has settled down, okay. Now the second scenario is the moment when B has settled down, on the floor, right? So when B has settled down on the floor, right, now there no longer be any resultant force. Okay, now when this happen, no resultant, no tension anymore, uh, or I can say that no resultant force acting acting on A. So there's no resultant force acting on A. Therefore, based on Newton's first law, A would continue with the same speed, which is the maximum speed, right? Now, therefore, A would continue to move at the constant speed of 3 meter per second. Okay. Now, since it will move at the speed of 3 meter per second, therefore, we would make a conclusions saying that the object B, when it's about to touch the floor, it would have already reached its maximum speed, which is the same as 3 meter per second here, right? So while the string is still taut, B has reached a maximum speed of 3 meter per second, which is the same as A. All right, now that is the brief explanation as to why the speed of B when it's about to touch the floor is 3 meter per second here, right? Now let me show you how the motion of these two particles actually look like. Okay, now let me, okay. All right, now there you have it. Okay, this is how it looked like. So when B is about to touch the floor, it would have reached a maximum speed of 3 meter per second, which is exactly the same speed as the object A. Okay, now if the speed, you can use contradictions to prove that if the speed of B when it's about to touch the floor is not 3 meter per second, therefore object A would not be moving at a constant speed 3 meter per second when it reach the pulley there, right? Now I hope the first question we are clear on that. I'm going to show you the second section shortly. All right, now let's take a look at the second section here. Okay, now let me show you the simulations of the whole mechanics again. Right, now since we have answer number one, now we can make use of the informations that we obtained from section 1 to answer section B, which we need to find the value of the height in this case. Right, now let me try out the simulation one more time. All right, so you can see that while the string is still taut, both of them will be moving with the same speed there. All right, now while the string is still taut, now the final speed of B when it's about to reach the floor is 3 meter per second, and then at the same time the speed of A would also be 3 meter per second here. So the speed of A is also 3 meter per second. All right, so I hope that is clear. Now, initially, the speed for the object B was a 0 here, okay, meter per second. All right. All right. Now from here, we can actually obtain the height just by using Suvet equations. But the only thing we don't know of is the acceleration. So therefore, we have to work out the accelerations before we can find out what is the height h here. So we need to figure out what is its acceleration in this case. Now to do that, we have to solve for Newton's second law. Okay, now we can consider. Okay, now let me Okay, let me rewind that again so that you can see what is going on here. Okay, while it is there. Okay, now we have the tension of the string which is acting upward here, and then there is the weight of the particle B, which is given by, in this case, is 1.5 Newton. Okay, so that will be the weight for particle B here. So this is B. Just label this so that we can differentiate A and B here. Okay, whereby for A, it has a weight of 3.5 Newton here. It also have the same tension as experienced by particle B also. All right. Okay. Now, generally, the drawing of the forces in the diagram is always look something like this. But of course, the complete um, diagram that represent the forces acting on the system should be, if you are talking about the whole system itself, so there should be a tension acting on the pulley itself in the opposite directions due to Newton third law here. All right. Now, before we begin, we're going to consider. All right. So we're going to consider the forces. So consider forces acting on B first. Okay, so we're going to consider forces acting on B by using Newton's second law. So here I'm going to write down in short Newton's second law. Now, therefore, we have 1.5 subtract off with the tension. Therefore, it will produce an accelerations downward. So the accelerations will be 0.15 kg acceleration here. Now, bear in mind, since the string is still taut, the acceleration experienced by B must be the same as the acceleration experienced by A also. Okay, now that will be our first equation here. Right. Now next, we're going to consider the forces acting on A now. Okay, we're going to consider forces acting on A now. Okay, now since the surface is smooth, therefore there is no frictional force here. The only force that is acting on particle A is just the tension. And then therefore the tensions would produce the accelerations on the particle A here. Okay, now that would be 0.35 A. Now that will be our second equation here. By solving 1 and 2, okay, now take for instance, we can take 1 plus 2 here. Okay, now therefore we will get 0.5 A equal to 1.5 there. Therefore, the accelerations will be 3 meter per second square. Right. Now we have successfully identified the accelerations downward that is experienced by both the particle A and B. Okay. For particle B is downward, for particle A is towards the right hand side. All right. Okay, now I hope that is clear. Now next, in order to find out the height itself, we're going to use the Suvet equation. So by using one of the Suvet equation, we're going to consider um, the motion of B in this case. So we are only interested in the motion of B. By using one of the Suvet equations, V square equal to U square plus 2AS here. All right, whereby the S itself represent the height in this case. Right? Now we know that the final velocity is actually equal to 3. Okay, so that will be 3 square. Initial was 0 because it was released from rest. Okay, and then the accelerations we have already found that, which is a 3, and then that will be our height there. Right? Therefore, in this case, we will be able to identify the height as 1.5 meter here. All right, so I hope that is clear for these questions. Now I'm going to move on to the next question shortly. All right, let's take a look at question 3 now. A car of mass 860 kg travels along a straight horizontal road as shown in the diagram there. Now the power provided by the car's engine is P. Okay. Now it's just that in my diagram I'm using D representing driving force. Now there is a relationship between the driving force and the power of the car engine. Now, the resistance to the car's motion is R Newton. Anyway, in my diagram, I'm using Fr to represent the resistance to the motions of the car. Now, the car passes through one point with a speed 4.5 meter per second and accelerations of 4 meter per second square, as shown in the diagram also. Now, the car passes through another point in another time with a speed of 22.5 meter per second and accelerations of 0.3 meter per second. It seems like it's uh, picking up speed but does not accelerate, okay, faster than before, right? Now the task here is we need to find the values of P and R, which is the power of the car engine and the resistive force, which I represent that as Fr. Right, now let me show you how the motion actually look like. At one point A, it has a property of velocity 4.5 and acceleration of 4 meter per second square. Now you will see that it will move along the straight road and then reach another position at another instant of time where its velocity increases, but there's a decrease in its acceleration. Okay, now we make assumptions that the resistive force remain the same throughout the motions from A to B, and then the driving force would depend on the speed of the car itself at that instant of time, right? Okay, now whenever there's a questions involve power, now we need to make use of this formula here. Okay, so I'm going to write down the formula at the side that we need. So one of the formula that is very important is power is actually given by the driving force. In this case is a driving force multiplied with its instantaneous speed at that position itself, right? So we're going to make use of this formula to solve this problem here. Now, we're going to consider this. Consider um, the um, the motion of the car at position A here. So we're going to consider the motion of the car at position A, right? Okay. Now, by using Newton's second law, right? As long as the questions involve forces, so therefore you must think of Newton's second law here. Right. Now we have the driving force. Subtract off with the resistive force. Here I label my Fr as resistive force in this case. So that is basically D minus R, and then it will produce a certain acceleration M A here. Okay. So the first one is its acceleration is given here. The speed is given at this point of time here. All right. Now, by using this formula here, we can find the relationship between the driving force and the driving force and the power itself. So therefore, I'm going to convert this here, the driving force, into. So if you rearrange this, you will notice that the force itself, or the driving force in our case, is power divided by the speed itself. Therefore, we can change this driving force to power divided by its instantaneous speed equal to ma here. Okay, so I hope that's clear. Right, now from here at position A, we don't know its power, but we do know its speed as 4.5, and then resistive force we are not sure, but mass is given 160, and then its acceleration is 4 meter per second square here, right? So therefore, this one will be 3, 4 or 3440. All right. Now, of course, at this point, we can try to arrange this algebraically so that we can obtain a much nicer linear equation here. So we have 4.5r and then 4.5 multiplied with this one here. All right. Okay. I think it's better if I use my calculator just to calculate this, right? In case I make any mistake with this. Let me see. 3440 by 4.5. Okay. Now that would actually give me 15,480 here. All right. So just let me check for a while if I got everything's correct. Okay, now there you have it. That's our first equation. Then we're going to perform or repeat the same procedure again by consider the motion of the car at position B. So position B, we're going to repeat using the same Newton's second law. We will end up with P divided by the speed is 22.5. Also subtract off with the same constant resistive force, 860 here, and then acceleration is 0.3. All right. So from here, we will get what do we have here? Let me see, 24, 25, 8. Okay, just let me check if I got that correct. Okay, so 258 there, and then again we can rearrange this nicely. 2.5r. Okay, and then therefore, let me see, what do we have? Okay, we have 5805. Now that will be our second equation. Now, of course, getting the P and R will be very much a piece of cheesecake in this case. All you need to do is just solve equation 1 and 2 easily. So in this case, I'm going to take 1 subtract 2. Okay, therefore I will get, let me see, is 18r. So 18r is equal to, all right, let me get this properly, 1515480. All right. So therefore we have a 9675 here, and then from here we should be able to obtain the value for resistive force quite easily, which is the same as, let me see here, uh, is it the same as this? Okay, let me check. I think I got it wrongly. Okay, just let me check the value one more time. 1515480, and then 5805 here. Okay, then 9675. Okay, 9675, correct. So I will end up with my resistive force equal to 537.5 Newton. All right. And then by using the answer for resistive force, I will be able to, I can substitute this back to any one of these equation here. For instance, I'm going to use equation 1 here. Therefore, the power developed by the car engine, since it is, we also make assumptions that it's a constant power produced by the car itself, right? So therefore, this would be, hold on, let me see. All you need to do is just take 1,500, sorry, 15,480, add up with 4.5 there. All right. So we're going to use that first equations here. All right. Okay. So just hold on. Let me write that down. So from here, there will be 4.5 R. So that's my R here. And then add up with 15480 there. All right. Now let me see what do I have here. 4.5. Okay. And then finally that is, so here I will get 2418.75. add up with 15480. Therefore, I should be able to obtain the final value for the power. Okay, let me get this correctly. 2418.75, 2418.75, and then with 15,480, and then that would yield 17,898.75 watts. Okay, now that will give you an idea how to actually solve this mechanics question using simultaneous equation and this formula that involve power and its forces. All right, I hope that is clear. Now we're going to move on to the next question shortly. All right, let's take a look at question 4 here. We have a lorry of mass 12,000 kg move up a straight hill of length 500 meter according to the diagram here, starting at the bottom with a speed of 24 meter per second and reaching the top with the speed of 60 meter per second. Now the top of the hill is 25 meters above the level of the bottom of the hill itself, so as labeled here also. Alright, now the resistance to the motion of lorry is 7,500, right, which is given by this variable F here, so frictional force, or the combinations of the frictional force and the air resistance, which provide the resistance to the motion, that amount to 7,500 Newton. And now our task here is to find the driving force of the lorry, which is D here. Okay, we have the weight component here, W, and then we have the normal force acting on the lorry itself. Right. Now, before we start with this, I'm going to show you what we are looking at here. Right. Just let me show it to you. The lorry would actually move from the bottom of the hill up to the top of the hill. So here I label as P, and Q here. It travel through 500 meter along the slope. Okay, let's take a look. Okay, now you can see that while it's moving up the hill, the frictional force is assumed to be constant. There is a driving force there, which we also assume to be constant here. And then it has the weight component and the normal itself. Right. Now this is the setting of the mechanics. Now, how are we going to solve this? Okay. Now, generally there are few methods here, so I'm going to show you some of the methods that is available to access or to analyze this situation here. Method number one, we're going to use the work energy principle. Okay, so I'm going to write it down here. First method, work energy principle. Okay, so work energy principle state that the amount of work done is equal to the change in kinetic energy. Right. So that's what it meant here. Okay. Right. Now, we are able to evaluate the change in kinetic energy here, which is given by these two parameters here. So that is actually given by half. We knew the mass itself. Okay, so that is basically m. We have to take the final velocity minus final speed minus of the initial speed here. So that will be the change in kinetic energy. Okay, so I hope that is clear. And then that will give us the work done. So here I'm going to evaluate this value here. So we have 12,000, and then the final speed, and then the initial is 24. All right, so that would actually give us like 6,000 by the -8, and then by 40 here. Okay, generally we will get let me see, 17. This is 32, so 32, that will be 1 32, that will be 192, sorry. So that will be a 192. So let me erase that. So 192. Now 32, 192. We have 1, 2, 3 here. Okay, so that will actually give us um, 1.92 million joule. Okay, let me see whether I got the numbers correct. So 1, 2, 3, 1, 2, 3, 4 here. So you have 32 here, and then that will be 19.2. Yep, correct. So that is 1,920,000 joule here. Now that will be the change in kinetic energy. Now there's a negative sign here, which signify that there is a loss in kinetic energy due to the frictional force um, and the weight itself. Right. Now, work done. Okay, once we have done with evaluating the change in kinetic energy, now we have to focus on the work done. Okay, what are the work that the lorry has to carry out in this case? All right. Now, either the work done is provided uh, to to the lorry itself, or whether the lorry need to have extra energy to overcome that um, resistive force. We're going to look at that, right? So work done here, the second part we're going to work on is the work done. So work done is basically given by the resultant force multiplied by the distance travel along the directions of the resultant force. Right? And then the resultant force that we have here is given by D minus F, which is the frictional force. And then at the same time, there is also a work done to overcome gravity. And then this component is not along the slope, so we have to resolve this weight component along the slope. Right? So that will be uh, W sine theta multiply with the S here, right? So once you are comfortable with this, well, we're going to substitute all the values available. Of course, except the D is, D is the one that we need to find, which is the driving force. So we knew about the resistive force, which is 7,500, and then the weight is 120,000 by the sine. So the sine is actually given by, okay, here I'm going to write it down. Sine theta is actually given by 25 over 500. Okay, so that is typically 1 over 20. So we're going to write it down as 1 over 20. And then finally, I'm going to multiply by the distance travel, which is 500. Right? And then this whole result here, now we can actually simplify a bit. So let me simplify before we go to the next section here. So let me see here. So that will be 6,000. 6,000, that will be 13,500 by 500. Okay, so that's how it looked like. And then this work done based on the work energy principle should be the same as the change in kinetic energy. Therefore, we have D by 500 is equal to 1920,000 here. Right. So from here, we will be able to obtain the D itself. So let me do it slowly. So we need to divide by 500 here. So we have um, 15 here, 42, 8, 4. So add 4 or 0. So that will actually give us a negative 3840. Therefore, the driving force will be 13,500. 13,500 minus 3840 there. And then that would yield 9, let me see here, 9660 Newton. So therefore, the driving force required to move the lorry from the bottom of the hill up to the top of the hill, having a speed of 60 meter per second, should be 9,660 Newton here. Okay, so what we are using here is method number one, which we call it as a work energy principle. All right, now I hope that's clear. First method. All right, now next I'm going to show you the second method, how we can attempt this mechanics problem here. All right, let's take a look at the second methods. Second method is quite similar to the first method, but here I don't really call it a work energy principle, but instead I would give it a general name, conservation of energy. Okay. Now, the way we apply conservation of energy here is more explicit compared to the work energy principle, which was derived from conservation of energy, actually, right? So, by using conservation of energy, usually based on my methods here, I would say that the total energy at position P must be the same as the total energy at position Q there. All right, now that's how I would like to present that. All right, and then at position P, we only have kinetic energy. So I'm going to write that down. Kinetic energy, okay, which is given by this speed here. And then at the same time, at the bottom of the hill, there will be a driving force. So no, work done by the driving force. Now, bear in mind, you may think that work done is something different from energy. It is not. All right, work done require energy, and then this energy is given by the engine itself. So initially, for the lorry to be able to commute up the hill, the engine is providing an energy for the lorry to be able to move up. So this part here you can treat as energy provided to the lorry. Okay, and then as you go up to the hill there, all right, now you need to overcome some of the loss in energy. So due to okay, so at position Q, we know that there is a kinetic energy. So we're going to write that down, kinetic energy. At the same time, this truck here sort of gain gravitational potential energy also. So we will write down that mgh, because at Q it has a gravitational potential energy, it has kinetic energy. At the same time, all the energy provided by the lorry itself is being converted to work done against the resistive force. Okay, so there's also a work done by the to overcome the resistive force. Right? So, or the work done to overcome the resistance to the motion itself. And then there you have it here. Right, now you will notice that here I do not include the work done against gravity, which is actually okay. Now maybe I would like to write this way, then it will be easier to see. Okay, now there's actually half mv square, and then at the same time there will be a work done against gravity, so that is basically w, w sine, because it is at the is along the slope here. So this is actually work done by the gravity, which is sine theta multiplied by the distance travel, and there's also work done against the resistant force here. Okay, now I can rewrite this again. I don't want you to confuse here. Okay, now we have a driving force. Yes, these are all the same. Now you will notice that this part here is very important. This part here, work done to overcome the gravity, is actually what we known as the gravitational potential energy. So generally, this term is actually gravitational potential energy. So you can actually write it down as a gravitational potential energy, and then finally we have the work done against the resistance. Okay. And then from here, all I need to do is just substitute all the value available. So for instance, okay, now 12,000 here by the initial speed, 24, And then after that, my driving, I have no idea. So 500 here, 12,000. And then by the final speed, which is 16. And then you have G, which is 10. And then the height reach is 25 here, right? And lastly, I will need to include the resistive force, which is 7,500 by 500 here. Okay, so you can see this is what is going on here. Okay, now if I try to divide everything by 500, okay, I just want to simplify this whole thing here. So I would actually get, let me see, that will be 60, that will be 12. So that'll be 12 by 24 square by D, because I divide everything by 500 here. So therefore, this will also be 12 by 16 square plus, okay, this one will be 24 instead, by 10 by 25, and then finally I have the 7,500 here. Okay, and then therefore my D would be, uh, is it 12? Hold on, let me check here. This is 12. Yeah, correct. Okay, so at the end of the day, I would have okay, I can move this over here. So if I try to simplify that, that will be 12 by 40 by negative 8 there. And then what I have here would be, let me see here. Okay, let me do a bit of math here. All right, 128.4 here. That will be 600. Okay, 6,000 here. Okay, now there will be 6,000. So 6,000 over here. Add up with this. So 1,000. Sorry, 13,500. And then this part here would be 48. Okay, 48. That will be 48. Did I get it correct? Okay, 32 here, 0. We have a 12 here. 64, 2, 3. So 3840. Okay, so this part will be 3840. All right. So from here, I will get 13500 here. And then, of course, you knew the number. You have seen it just now, which is exactly the same as 9660 Newton there. Right? So this is also another way of uh, solving these mechanics questions through the idea of energy. Through the usage of energy, you can either use conservation of energy, whereby its intention is more explicit. If you use work energy principle, that is actually the one that has been repackaged so that it's easier to approach the problem. Personally, I would say that yes, work energy principle is easier to work with. There's less confusions involved, right? Unless you are very familiar with conservation of energy, right? But conservation of energy does have its pro when the context become more complicated, right? So I hope that is clear. I'm going to show you another method how to solve it using kinematic and Newton's second law, right? Okay, we're going to take a look at it. Okay, now we're going to look at the third methods. Okay, so the third methods, I'm using the forces method. May the force be with us, right? So we're going to apply kinematic, okay, and I would say Newton uh, second law, right? In this case, we'll be using Newton's second law instead, right? So I hope that is clear. Okay, how are we going to deal with this? Okay, now first of all, we will need to figure out what is its accelerations up the hill. Now, of course, I shouldn't be using the word acceleration here since there is a decrease in the speed itself. Most probably, you will encounter a value negative for the acceleration, which basically refer to deceleration here. Okay, now to do that, I will make use of one of the Suvet equation. For instance, I'll be using these Suvet equations, which will be easier to get used to, because the only thing we need or we are interested to obtain here is the acceleration. We are given the distance itself, distance travel, which is 500. And then we have the final speed and the initial speed. So therefore, we should be able to obtain the accelerations here. So I'm going to apply this here. Let me rewrite that again. Okay, so my final speed is here. My initial is here. I'm interested to get the acceleration. Distance is 500. Okay. So from here, I'm actually getting the 1000 A here. I get by 40. Okay. So therefore, my acceleration in this case is negative 0.32 meter per second square. All right. So I hope that is clear. That's how we get the acceleration. Okay, we are done. That's the first start up. So once we have done that, now we can consider forces acting on the lorry. Okay, consider the forces. Here it include driving force, frictional force, the weight, and then the normal force in this case. Right. Now, when we consider forces acting on the lorry, the one that we are interested to work with is along the slope. So here I'll just put down along the slope. So we are only interested in the component of force that is acting along the slope itself. So therefore, that will be okay. So the resultant force is given by this, and then this resultant force should produce an acceleration based on Newton's second law here. Okay. So I'm going to write down this is Newton's second law. All right. And then driving force, which I have no idea, but I do have the resistive force. The weight component, 120,000 by sine. We have already determined the sine previously, which is 1 over 20 here. And then this is 12,000 mass, and then acceleration is negative 0.32. Okay, so from here I would get myself 13,500 here, and then that should be equal to 1, 2 here. Let me do the math one more time here. 64023 there, so 2840. So negative 3840 here, and then therefore you knew what is coming next. So that will be, oops, I keep on writing the wrong number here. So 3840, and then therefore that will yield 99099. Okay, so that should be 9660 Newton here, right? So all of these methods will work generally if you follow the rules closely, right? So I hope you are clear how to actually approach this mechanics problem, right? I'm going to move on to the next question shortly. Okay, question 5 is about resultant forces of core planar forces. In this case, we have 1, 2, 3, 4. 4 core planar forces here, right? Core planar forces basically means the force is acting on a two-dimensional plane in this case. It's not actually acting in a three-dimensional plane. If it were in a three-dimensional plane, then we will have to have more informations. This informations displayed here is not sufficient for us to work with three-dimensional forces, right? But we are dealing with two-dimensional forces only. Now, all the magnitude of the forces are given here. Okay, so they are arranged in a very neat descending order magnitude here. I think it reduced by 4. Okay, that actually gives us arithmetics sequence here. All right, that's very interesting. Or if you read out from the bottom to the top, it's an increasing arithmetics sequence here. So the person who actually designed this is very creative in a way. Right. Right. Now the directions is shown here. Now we need to find the magnitude and the direction of the resultant force of the four forces here. Okay, acting at a point. So the point that all the forces is acting is here. Okay. Now the usual way is you can. There are two methods here. So I'm going to show it to you. The two methods. The first methods is my favorite, vector. So I'm going to use the first method, vectors. Okay. By using vectors, I'm going to resolve, or I'm going to represent each one of these forces in its vector form, making an assumption this is in two-dimensional, and then this section represent the x direction, and then this part here represent the y direction, or the vertical directions, horizontal direction here. Okay. Now I'm going to use the conventions of right now, since this is the smallest one, so we'll start from F1, F2, F3, F4 then. So maybe I'll label this as F1, F2, and F3, and F4 here. Okay, now we're going to represent each vector in its vector format. So the first force, now there's only horizontal component, 4 unit to the right. So usually we represent the horizontal component first. So 4 units to the right. There is no vertical components there. So therefore, the force number 1 can be represented in its vector form this way. So we read an x component, y component, and then we can repeat that for force number 2. Now we have to resolve this component here along the x direction and along the y directions there. So therefore, in this case, it has it's actually moving to the right, certain units to the right, and then certain units vertically upward. So therefore, by resolving that, we have um, the x component, that will be x cos 30, and then the vertical component will be x sine 30. All right. Now, if you're comfortable with this, with your calculator, or if you can by heart the spatial angle there, we will get 4 sec 3 here, and then that will be a 4. And then that will be our second representation of the force. And then the third one, we have now the same thing, which is 12 cos. You just have to be careful a bit. Now we are looking at a 60 degree now. So that will be cos 60, and then sine 60. All right. And then cos 60 is a half. So therefore 6, this one will be 6 sec 3. And then there you go, that's the third one. And then of course lastly is the easiest one. There is no x component there, but it has a vertical component of 16 unit. And then there you have it. These are all the forces. Right now, as they mentioned, resultant force of the four forces. So resultant means the sum of all the forces. That's what it actually meant. So resultant means the sum of all this. So all you need to do is just arrange them. Okay. This is 6, sorry. And then finally you have 0, 16. Now, and then of course, if I arrange it in its exact form, that will be 10 plus 4 sub 3, and then the other one will be 20 plus 6 sub 3. Mhm. Okay, now generally there's a full package of the resultant force. Okay, but if you need the magnitude itself, okay, if you need the magnitude itself, okay, um, okay, so the magnitude, okay, now maybe I can rewrite this with a simple symbol here instead of using the summation symbol. I can just write down the resultant force as this. So therefore, if you are interested to get the magnitude of the resultant force, okay, that is basically 10 plus 4 sub 3, a square, plus 20 plus 6 sub 3, a square there, and then therefore we have to square root this. All right. Okay, let me get my calculator here, and then let's see what do we have. Okay, we have 10 plus 4 sub 3. Okay, 4 sub 3 there. And then we have 20 plus the 6 sub 3. Okay, so therefore that will be a square root of the a square, um, end up with the b squared. And then that would actually yield, okay, this answer will be 34.8 then. I'll leave that to the nearest three significant figures. Now the magnitude of the force is this, and then the direction. Okay. Now, generally, if you look at this, most probably, okay, now the resultant force, if you were to draw another diagram here to represent the component of the resultant force, now therefore, if this is our x, and then this part will be our y here. So the resultant is this one will be approximately 14 units to the right, and then that will be like um, 27 units to vertically upward. So most probably the resultant force would look something like this. So the resultant force will look something like this. Okay, so that will be our resultant force. Okay, so this one will be our resultant force. And then it has a magnitude of 34.8 Newton here. Right. And then it has a vertical component here. Its vertical component is 20 plus 6 3. 20 plus 6 3, which is 20.39. And then it has a horizontal component here, which is the 10 plus 4 sub 3 there, right? And then you can use a very simple reference to the horizontal, for instance. This is the angle. So we can actually calculate the angle by taking a tangent. So the tangent will be 20 plus 6 sub 3, 10 by sub here. And then, of course, the angle could be obtained easily by taking the inverse tangent here. I just write down the full notation. That will be okay. So based on my calculator here, okay, hopefully I got it correct. So that would be arctangent. We are looking at the b divided by a there. Okay, so the angle uh, is 60.9 then. So I'll write down 60.9. Right. So therefore, finally, you can conclude that the directions of the resultant force make an angle 60.9 from the from the horizontal. So it actually make an angle of 60.9 uh, to the horizontal or from the horizontal itself. Right. So I hope that is clear for this question. Okay. Now, that is one way to attempt it. I'm going to show you the second methods. All right. All right, now the second method is by using resolutions of forces. So resolving, yeah, correct. Okay, so resolving forces into the horizontal and vertical directions. So the horizontal and vertical directions that I'm talking about is still the same here. So that is horizontal. This is considered as vertical here. So we're going to resolve that into their respective components. So the first one, we're going to focus on the the horizontal direction. So in the x direction, so here I just label in short. So in the x directions, we're going to refer to each one of these forces. So now we have a 4 Newton. So the Fx is actually 4 Newton, like this. Okay, 1. So that is the first. This is the first force. This is the first force, 4 Newton to the right. So I just labeled it as x1 here. Okay, and then the second one, this is F2. This is F3, and then you have F4 here. So therefore, the second one will be F x also, because we are dealing with the x component here. So the second one, the second force. So the second force here, the x component for this is given by 8 cos 30, which is actually 4 sec 3 Newton. Okay, and then we can repeat that for the third force, which is 12 cos 60 in this case. Okay, so that will be a 6 Newton, and then finally we have the x4. So x4 is very simple, it's just 0 Newton because there is no x component for that. Right, now okay, next one we're going to resolve it in the vertical component, then y. Okay, by doing the same approach here, so I will have my y1. Okay, my y1, there is no vertical component. And then next, my y2. Okay, my y2 here, that will be the 8 sine 30. And that will be a 4 Newton. And then I'm going to repeat that for y3. So y3 is 12 sine 60. And then that would yield the 6 sec 3. Okay, and then finally I can work with my 4. 4 is the easiest one because there's only 16 unit, and then that's it. Okay, so I hope that is clear at this point. Now once we have done all this, all we need to do is to get the sum of all its x component. So the sum of all its x component is actually given by 4 plus this and this. So generally that would actually give us 10 plus 4 sec 3. And then repeating the same procedure for y, we found that we have 20 plus 6 sec 3 here. And then therefore the magnitude of the resultant force is basically the same as now let's for ease of calculation, I just call this A, this is B, so therefore that is actually A square plus B square square root. Okay, so if you refer to my my calculator here, just to show you again, since I'm using the same A and B here, you can see that if my A is this, my B is this, so the square root of this would yield 34.8 Newton. Okay, and then the same result here, so we can actually label this as X and then label this as Y one more time, and then you will notice that the resultant force would be something like this, just like before. So I just relabel that one more time. And then the angle made by this resultant force is here. This vertical height is given by 20 plus 6 root 3, and then this horizontal section is given by 4 sec 3 there. So therefore you can determine the angle quite easily by taking the inverse tangent. Inverse tangent 20 plus 6 sec 3 over 10 plus 4 sec 3. And then there you have it. We have already calculated that before. So 60.9 degree um, to the horizontal. Okay, so I hope that's clear. These are the two methods that you can actually apply to work with the resultant force here, right? Okay, I'm going to move on to the next sections of question 5. Right, we're still on question 5 here. Okay, I just label that one more time. This is still question 5. Okay, now the configuration of the forces acting on the point has been changed here. So you can see that from this figure. State the magnitude and the directions of resultant force shown in figure number 2 here. Okay, here I'll just use the vector methods here. So the only thing changes is the 4 and the 16 has been interchanged. And the rest of the force, yeah, 8 and 12 also has been interchanged here. So therefore, I will relabel this one more time since we start off from the smaller one. So we will label it F1, F2, F3, F4 here. Okay, now writing them in the vector form, we will have F1 as given as 0.4 Newton. F2 is same thing here. So we have 8 cos 60, which is a 4, and then 8 sine, so which is 4 sec 3, very similar to the previous one. And then my third force, is all over here. So that is typically a 12 cos, so that would be a 6 sec 3, and then 12 sine, so which is a 6 here. And then finally, the F4 is the easiest one to work with. It's merely just 16.0. Therefore, the resultant force will be given by the sum of all these forces here. That will be 0.4 here, 4 sec 3, and then you have 6 sec 3, and then finally you have 16.0 here. And then that would actually yield 26 sec 3, and then that will be a 10.4 sec 3. Now magnitude wise, okay, so the magnitude of this resultant force would still be the same or not? Okay, let's check that out. So that is the same as 20 plus 6 sec here, square plus 10 plus 4 sec 3 square. And then we're going to square root this. Okay, let me get my calculator one more time. Okay, so we can check here. The value are exactly the same. The only difference is the x and y has already interchanged. So if we take the square of this, add up with the square of this, we still able to obtain the same magnitude, which is 34.8 Newton. Okay, 34.8 Newton. Now the only difference now is the direction. The directions will be a little bit different in this case. Yeah, this is y. Now that would be a 20 unit over here. So most probably it would look something like this. Yeah. Okay, so it will look something like this. This is the resultant force, and then the angle will be a little bit different. So the angle is given by inverse of what do we have here? 10 plus 4 sec 3 over 20 plus 6 sec 3. Because this time the y is 10 plus 4 sec 3, and then the x is this. Okay, so that's how it look like. Let's check out our calculator. What do we have? Now that will be an arctangent of a divided by b this time. Now that will be much more smaller than before. Okay, so we can say that the direction is 29.12 degree from the horizontal or to the horizontal, right? Or you can actually use a bearing here. You can also say that it has a bearing of so the bearing is always measured from the north direction. So this is the bearing itself. So the bearing must be of 7 sorry, 70. What am I writing here? It's not 70. It's 60.88 degree, or you can say that approximately 0.6 0.661 degree approximately, right? Usually we put a zero in front just to signify that this is a bearing measurement. All right, so I hope that's clear. We have done question 5 now. We're going to move on to question 6 short. All right, let's take a look at question 6 now. Okay, now a small box of mass 5 kg is pulled at a constant speed here down a line of greater slope of a rough plane inclined at 10 degree here to the horizontal. The pulling force has a magnitude, so the pulling force is labeled as P, has a magnitude of 20 Newton and acts downwards parallel to the line of the greatest slope of the plane. Now the first question, find the coefficient of friction between the box and the plane. This is the questions that we need to answer here. What is the coefficient of friction? Okay, all right. Now let me show you how would that look like. Okay, now before that, the second part, the pulling force is removed while the box is moving at 2.5 meter per second. All right. So while it's moving, the the pulling force has been removed, but the friction will still be there. Right. So we need to find the distance moved by the box after the instant at which the pulling force is removed. Okay. Now we look at the first one first. I'm going to show you how the mechanics actually look like. Okay, let's look at this. Okay, it's moving down. Okay, so it's moving down along the slope. Okay, and then the pulling force is removed while the box is moving at 2.5 there. Okay, we're going to look at that shortly. We're going to work out the first question first. All right. The coefficient of friction. All right. Now to work with coefficient of frictions, we will have to apply the Newton's second law. Now before that, okay, this is the same as 10 degree here. All right. By resolution of forces here, okay, if we resolve it perpendicular to the slope itself, we will notice that the R, okay, so I'm resolving perpendicular to the slope there, okay, by considering the forces. Okay, I should actually mention that. Consider forces acting on the block. So consider the forces acting on the block itself. I'm interested to work with the force in this direction, perpendicular to the slope itself. Okay, so for this, I will be able to figure out my normal force must be the same as the weight cos theta here, and then that would be the weight is 50 and then cos 10 degree. All right. So that will be my normal force, right? And then I also know that my frictional force is actually given by the coefficient of frictions multiplied by R. Okay, this is a dynamic frictional force, so we assume that it has already reached a maximum in this case. Now, if you are looking at a limiting equilibrium, the actual formula for frictional force at a limiting equilibrium is actually this. Right. Okay. So as it start to move, it would have reached its maximum frictional force, which is actually given by mu 50 cos 10 degree here. Right. Now that will be the frictional force. Right. Okay, now next, by considering the forces again, we are going to resolve the forces along the slope now. Now we know that the blocks is moving down at a 0 uh, meter per second square acceleration. Why? Because it's moving at a constant speed. So constant speed, acceleration must be equal to 0. So that is very important facts that you need to remember. If it is moving at maximum speed or constant speed, then acceleration must be equal to 0. So from here itself, we can use Newton's second law one more time. So that would be a P, which is the pulling force, um, with the help of the gravity itself. Okay, and then going against the friction, and then that would actually produce the acceleration. Okay, so that's how it actually look like. But we know that acceleration is actually equal to 0, so don't forget that it's actually equal to 0. Therefore, from here, okay, what we're interested to find is the coefficient of friction. So I'm going to substitute everything that we have. The pulling force is 20. The weight is 50. So sine 10 degree. Subtract off with the frictional force, which is given by 50 cosine 10 degree. Now at this point, I will not tends to key in this into my calculator because I want to get a value that is as accurate as possible when I reach the end of my analysis here. So that should be is equal to 0. Okay, so from here, all you need to do is just rearrange that, and then remember what you are trying to find. We are trying to find the coefficients of friction. So therefore, by rearranging the coefficient of frictions here, we will get 20 plus 50 sine 10 degree divided by 50 cosine 10 degree there. Okay, and then oops, that's a 50 cosine 10 degree. And then there you have it. That will be our coefficients of friction. So let me get my calculator here. Okay, so from here we have 20 plus the 50 sine 10. Okay, I need to divide that by what we have here. Hold on. Divide that by 50 cosine 10. Right, just let me check the number. Okay, so therefore, we will be able to obtain the coefficient of frictions. Right, now if you want to leave the answer to the nearest three significant figures, okay, I think my setting of my decimal places is only here, so I just leave it to 4 first, so it will be easier. Now, therefore, to the nearest three significant figures will be 0.583. Okay, so I hope that is clear at this point. This is how we find out the coefficient of friction. All right, so I hope that answered the first part. 5 marks there. All right. Okay, now we are done with that. So I'm going to write down whatever informations that we have obtained previously. So we have obtained the coefficients of friction, which is 0.583 here. We are going to use that for the second part maybe. All right, but I'm going to leave it there. And then there you have it. That's the first part. All right, so we're going to look at the second part here. Yeah, I accidentally erased off this value already. Just let me rewrite that again. I think mu that we have is 0.583 here. Okay, just for a reference. Now for second one, the pulling force is removed while the box is moving at 2.5. Okay, and then find the distance moved by the box after the instant at which the pulling force is removed here. So let me show you how does it look like here. Okay, so it will start to move down the slope. You can see that. Just hold on for a while. It's going to move down the slope, and then the okay move down the slope, and then the pulling force is being removed, and then after that it's going to slide down, and then it's going to stop somewhere because due to the frictional force, it's going to stop somewhere, assuming that it does not reach the bottom of the slope yet, right? So I hope you are clear what we are looking at here. All right, so we need to find the distance moved by the box after the instant at which the pulling force has been removed. So what we are looking at is actually somewhere here. Let me show it to you. So basically we are looking at somewhere here. So let's do it somewhere here. Okay, so from somewhere here, and then it stopped somewhere here. It stopped at somewhere here. All right. So we are interested to figure out how far it has moved between here and here. Let's label that as S. All right. So I hope that is clear. By the time, I think by that time, the pulling force has been removed. Let me see. Yeah. Okay, you can see that the pulling force has been removed at this instant until it stopped somewhere here. All right. Okay, now the same idea here, we have to work out its deceleration. Of course, in this case, definitely it's going to be deceleration. So we're going to figure out what is its acceleration until it reach at this position where its final velocity is actually equal to 0 meter per second. At the instant when it removed the pulling force, its initial velocity at this point is 2.5 meter per second, which is given here. All right. Okay, so I hope that's clear. And then I'm going to label this one more time. This angle is a theta, the same as 10 degree. All right, now we are ready. So by considering by consider the forces forces along, okay, not along, forces acting on the block along the slope, okay, along the slope itself. Okay, so therefore by applying Newton's second law, we know that there is no downward force anymore. The pulling force has been removed, but there is a frictional force. And then at the same time, there is also another component of weight, which is sine theta here. And then that would yield an okay, you can say that is a deceleration or negative acceleration in this case, right? Okay, now the okay, we knew about the coefficients of friction. So coefficient of friction is actually 0.583 here. Okay, so just let me roughly check whether it's 583 or not in case I copy wrongly. Yeah, correct. So it's 583. Okay, so the coefficient of friction is 583. We know that the frictional force is actually given by 0.583 R here. Okay, the R itself, whereby the R is actually given by W cosine theta. Okay, so W cosine theta. and then in this case the W is 50, cosine is a 10 there, right? So from here I can write down, I'm going to rearrange this nicely, so that is W sine, okay, I shouldn't write W anymore, W is 50, so I'll write 50 sine 10 degree minus of 0.583 R. So R is 50 cosine 10 degree. Okay, 50 cosine 10 degree, and then that would actually yield an accelerations which is given by this. Okay, so from here onward, you should be able to find its acceleration, of course. Okay, so that accelerations will be like 10 sine 10 degree minus 5.83 cosine 10 degree there. And then after that, I will need to take out my calculator at this point. So let me make it smaller a bit. Okay, so here what I have is 10 sine 10, and then I need to subtract off with 5.83 by cos 10 then. So therefore, that will be, I would say, approximately or quite close to -4 meter per second square. So that will be the deceleration as expected, right? And then lastly, I can use the kinematic equation or Suvet equation, as you like to call that. Find the distant move. Okay, so therefore I'm going to use this kinematic equation. All right. We know that the final velocity must be equal to 0. The initial was 2.5, and then acceleration is -4, and then distant move is the one that I'm interested to obtain here. Therefore, that is 6.25 over 8 there. So let me check with my calculator one more time. That will be 6.25 by divided by 8. So to the nearest three significant figures, I would say that is 0.781 meters. Okay, so I hope that is clear. That's how we solve this mechanics problem, right? So I'm going to move on to the next question shortly. Right, question 7. A particle P moves on a straight line. It starts at a point O on the line and returns to O 100 seconds later. The velocity of P is v meter per second at time t second after leaving O, where the velocity follow that cubic equation. Right, t is the time itself. Show that P is instantaneously at rest when t is equal to 0, t is equal to 50 seconds, and t is equal to 100 seconds. All right, now if you are able to sketch the graph, of course I have already sketched it here, you will notice that the only time the particle would reach instantaneously at rest is when its velocity is equal to 0. So you will notice that yes, it's 0 over here. And then it should be 0 at 50 seconds or so here, and then it should be instantaneously at rest at 100 seconds or so. So visually, yes, it does tally. Now, how do we actually prove that algebraically? Okay, so this is how we're going to do that. When it is instantaneously at rest, so instantaneously at rest when v is equal to 0. Okay, so when v is equal to 0 here, so all you need to do is just let this, is it 30, 1, 2, 3? Yep, correct. T cube, t square, right? Yeah, t square 5t is equal to 0 there, right? Okay, now from here onwards is basically up to you now. Okay, for me, I would like to remove all my decimal there, so I would like to uh, if you multiply by 1,000, for instance, if you do it, I would say here 1, 2, 3, 4. Okay, so you should actually multiply by 10,000 then. So if you multiply by 10,000, you should actually have this. That will be 150 t square. And then, of course, this one you multiply by uh, um, 1,000. So that will be, if you multiply by 10, there will be a 5, and then there will be a 500. Okay, so that should actually look something like this. And then factorization, of course. Okay, and then we can further factorize that one more time in this case. So let me see, we can do that by 500. Okay, so by 500 there. T minus 100, and then T by 50 there. So therefore we will get, yeah, we'll get 150 there. And then from here we found that T is actually equal to 0, 50, and 100 seconds. Okay, so the particle is at instantaneously at rest when T is equal to 0, 50 seconds, and 100 seconds. So that's the proof, right? So I hope that's clear, number one. Now, number two, find the values of v at the times for which the accelerations of the particle p is 0, and sketch the velocity time graph for p motions for t more than equal to 0 or less than equal to 100 there. Now, for the second one, now we have to recognize that this is actually a cubic equation. Okay, so yeah, okay, without the help of software, I'm going to show you shortly. Let's assume that you have never seen this graph. Okay, all right. Now we're going to look at second question here. So let me erase all this. We don't need this anymore. Now let's prove the first part. Find the value of v at the time for which acceleration is equal to 0. Now acceleration A is given by the rate of change in velocity, which is dv dt in this case. Now, therefore, if you differentiate this, 0, 0, 0, 3t square, and then you have 0 0.030t, and then finally you have 0.5. Okay. So when the acceleration is equal to 0, it means that when this is equal to 0, okay, now therefore we're going to solve this. So therefore that is t square, and then you by 10,000, 1, 2, 3, 4 there. So there's 300, and then plus 500. Okay, is it 300? Let me see. That is a 10,000 there. So that is a 0.300, and then that should be 30. Sorry, my bad here. This part would be 30, not 300. Okay, and then there you have it here. From here onward, we are going to determine the time first. Okay, let me see whether I'm able to factorize this correctly. Okay, let me do this very quickly here. 50, 10. Okay, is it 50, 10? Okay, 50, 10 does not guarantee that. 20, 20 and sorry, 10, 50, 50, and 10 does not work. Okay, why don't we try the okay, let me try one more time. I may not be able to figure this out at this point of time, but never mind, let's give it a try. That is the fun of doing math here. Okay, so maybe I can try like 25, by 2. Okay, 25 by 2, does it work? Sorry, 25 by 20, sorry. So 25 by 20, that will be like 60, 25, yep, that does not really work. The other one is 10, 5, 55. Hold on, 50, 10 does not work because this is, okay, this is 30 here. Okay, let me try if I have any other 100 and 105. Does it work? 105. Okay, if you have no idea, then we'll just have to rely on the, like for instance, sometimes I can't figure out, so all I need to do is just rely on my quadratic equations then. Okay, maybe I miss out something here, so that will be like 900 minus let me see, minus a 12 by 500 there, divided by 2, 3. Okay, I noticed that that is not, we are not able to solve that. Just let me check if I miss out anything here. Okay, so 4 here. So that should be 300. And then this one is 5,000. Sorry, I think I messed up here. Let me correct that one more time. That should be 3t square minus with what do I have here? I have 300 here, and then I have 5,000 here. Sorry, yeah, that should be a 5,000. Okay, and then from here, okay, from here, let me give that a try one more time. Okay, I think this is um oh, this is it 500 by 10? Okay, 500 by 10, or we could use the uh, let me see, 50 by 100. Okay, 50 by 100, there's a 5,000, or 50 by this. Does not work. 25 by 20. 25 by 20, 25 by 20, that is a 600. Okay, even that is a 60. I'm not able to figure that out, alright, at this point of time, so therefore, let me see whether I can figure that out or not. Okay, if I can't, I just have to rely on my quadratic formula one more time. Okay, that's very sad, huh? Okay, 435,000 divided by a 6 here. Okay, just check my calculator very quickly in case I accidentally calculated something wrong. Okay, cool, that's correct. Okay, so for this, okay, so for this it will be let me see here, 300 square, subtract off with 12 by 5,000. Okay, so that will be a square root of I. Okay, that will be that. And then because time cannot be negative in this case, right? So it doesn't matter in this case. This value is much more smaller here. So therefore, I'm going to work out the answer directly here. So 300 minus j. Okay, so divided by 6. Therefore, I will be able to obtain t is equal to 21.1 second, or the second one would be I can actually take what do I have here? I take the plus the j itself. So therefore divide by 6. Now I will be able to obtain. The second one is 78.9 seconds. So the time taken for the particle to have an acceleration equal to 0 are given here. Therefore, we are going to find the v then. So the v when t is equal to this. So at t equal to 21.1 second. So the v will be equal to, all we need to do is just substitute this. 21 here, sorry. So that is 21.1 square plus 0 0.5, 21.1. Yep, okay. Now using my calculator here, so let me try that out. 21, which is L. Okay, I should be using my G here. Okay, so therefore, the velocity at t equal to 21.1 is actually equal to 4.81 meter per second. And then I can do the same for when t is equal to 7.8, 78.9 here. So the v will be equal to the same idea here. Alright, so all I need to do is just, I'm going to rewrite that one more time. 78.9 cube. Okay, and then therefore, based on my calculator here, it should be Gn. Okay, that would be a negative 4.8 or 4.81 meter per second there. All right, so I hope that is clear at this point. So you can see that it changes direction. So you can see that it changes direction. Now I hope you are clear on this question here. Now we are not done yet. We still need to sketch the graph. Okay, now sketching the graph. You have already seen the shape there. We have already seen the shape. So it shouldn't be that tough at this point. So if I were to sketch this, first thing, I must label my axis. So this is the velocity. So velocity meter per second here, and then this is time, right, starting from 0 here. Okay, we know that it is instantaneously at rest at 0, at 50, and then at 100 here. So that is pretty obvious. It passes through here, and then it is also instant. Um, it also have a zero acceleration, zero accelerations at 21.1 around there. So therefore, it should be around somewhere here. So, and then you also have another acceleration equal to 0 at 79.0, somewhere here. Okay, so this is where its gradient is usually equal to 0 there. So therefore, if you want to sketch this, okay, it will look something like this. Alright, so whereby this actually refer to, this part here refer to 21.1, this part refer to 78.9 there. Alright, so I hope that is clear. And then at this point, its velocity, you may want to show that this is actually 4.81 here. This part will be negative 4.81. This is where it changes direction. Right. So I hope you are clear on second part of this question. Right, we're going to look at the last one shortly. Right, section 3 of question 7 here. Now I'm going to display the graph one more time that we can or we have drawn just now. Okay, it's just that I display it using the software itself. Okay, now bear in mind it start off from the origin, from O, and then for number 3 here. So it start off from all here, for instance, this is all. And then let's assume that it travel towards the right hand side. So it's going to travel this direction, okay, for 50 for 50 seconds. So at t equal to 50 seconds, it will start to change direction. It will start to change direction. Okay, because this is where is instantaneously arrest. That is when it start to change direction. That's the reason why your velocity become negative now, because it's moving in the opposite direction. Okay, and then after that it should move somewhere here, I assume. Okay, it will move somewhere here and then reach another positions like 100 seconds later. Okay, hold on. So I would use t equal to 100 seconds later, it would start to change directions again. All right, it will start to change direction again. Now, the only thing that I'm not very sure is I'm not sure whether it has reached zero, the return back to its original position before it changed direction, or it could have changed direction somewhere here, for instance, just before. So the distance travel from here to here, for instance, the S2 here, or the S2 could be referring to this. Either one of this is actually given by this area here. So this is S2. And then the distance travel from here to here, that is given by S1, which is this area. All right. So that is S1 here. Okay. Now let's try to find the distance travel S1. So distance travel S1 is basically the integrations from 0 to 50 there, v with respect to the time there. All right. So from here, the integration shouldn't be that tough to work with. It's typically this 0.01 divided by 4 t4. Okay, 3 0.005 t 3. Okay, don't forget that we increase it by 1, and then this one will be okay, I'm gonna write so that one will be 0.2, so 0.25 t square. And then we are actually integrating this from 0 to 50. Okay, all we need to do is just substitute this into here. So for instance 50, now that will be 0. Okay, I'll just substitute that directly here. Okay, yeah, I'm going to write it down here, it's easier. Okay, so once you substitute the 50 here, okay, I'm going to erase this. I'm going to get back to my software here so it's easier to work with. Now all I need to do is to is it my GX? Yeah, I think it's my GX. Okay, so that will be my GX from okay from the start is 0 and then to 50. All right. Now therefore you can see that the area obtained here is shown here. So there's the area. The first area is 156. Of course, you have to substitute this into here. You should be able to get 156.25 meters. And then of course, you may like to check when you change direction. Okay, will the distance be the same as S1 or not? So we are also very curious to find out. So for S2, that is typically, all right, now here you have to put a modulus sign because the area under the graph is below the horizontal axis. Now that will be from 50 to 100 there, v dt. Okay, now the same idea here. All you need to do is just substitute the 50 and 100 there. Now I'm going to calculate that directly from here. You can do it on your own, shouldn't be that tough. So I'm going to have the g function again. So from 50 to 100. Okay, now you can see that both the area are exactly the same. So both the area are exactly the same. 156.25 meters. So which means when it changed direction, it has returned to its original position because both the distance are exactly the same, right? So you want to find the greatest distance of P from O. So the greatest distance would be greatest distance from O. Okay, let me read that one more time. Find the greatest distance of P from O for 0 to 100 seconds. So greatest distance. Okay, now you can see greatest distance from O itself must be 156.25. The total distance will be twice of this. Okay, let me write that down also. Total distance. Uh, Total distance, I'm talking about total distance from 0 to t equal to 100. So total distance for t 0 to 100 is twice of that. So that will be like, so twice of that will be 312 approximately. 312.5. 312.5 meters there. Right, so I hope that is clear for the last sections here. Right, I'm going to move on to the next question shortly. Right, question 8. Three small smooth spheres A, B, and C of the equal radii, which means it's the same radius, and of masses of 4 kg, 2 kg. So particle A is 4 kg, particle B is 2 kg, particle C is 3 kg respectively. Lie in that order in a straight line. There's a straight line on a smooth horizontal plane. Initially, B and C are at rest, and A is projected towards B with a speed of 6 meters per second. After the collision with B, after the collision with B, A continues to move in the same directions but with a slower speed. Now find the speed of B after the collision, after the first collision. Now I'm going to show you how does it look like here. Okay, you can see A move with the speed of 6 meters per second and then collide with B, right? Collide with B there, right? And then right after the collision, A moves with the speed 2 meter per second. So 2 meter per second there, right? So let us look at how do we work out on this. Okay, now in terms of collisions, so we'll have to apply conservations of momentum. Okay, so we're going to use the conservation of momentum. All right, conservation of momentum state that the total momentum of the entire system remain constant for a closed system, which means there's no external force acting on the system itself, right? So here, total momentum before collision. Before collisions would be 4 kg multiplied by 6. So that is before. We assume that this direction is positive here. So therefore, that's the only momentum before, and then it must be the same as the total momentum after. After, okay. Yeah, yeah. By the way, if I want to show you the actual conservation of momentum, there is a momentum contributed by the first particle A, and then there is no momentum contributed by B because initially B was 0. So mathematically, it means something like this. And then after the collision, A move with the speed 2 meter per second. So A is 4. It move in the same directions also, 2 meter per second. And then we are interested to find out how fast is B after the collision. So therefore, I'm going to write down B. So what will be the speed of B here? So that is pretty direct calculations here. So you can see that there's 24 by 8 there. So that would be like 16. Therefore, the speed of B after the collision must be 8 meter per second. So the speed of B, speed of B after first collision is 8 meter per second. So B will be moving 8 meter per second, and then A will slow down, and then it will still be moving at 2 meter per second here. And then B will be moving towards C. Most probably it's going to collide uh, with C. Right? We're going to look at question B shortly. All right, so for section B, sphere B now collide with C. Okay, we know that after A collide with B, B will be moving towards C now, and then it will surely collide with C because the plane is smooth. Right, so it should be moving at a constant speed of 8 meter per second, the one that we have calculated before this. Now in this collision, these two spheres when they mention these two spheres, I believe they refer to B and C. Coalesce, meaning that they combine and join together to form uh, as a one body to form an object D. So BC join together, we call that we call that body as object D. And then we need to find the speed of D after the collision. Okay, now let me run the simulations here. So just to show you again, this is after the first collisions now. Okay, you can see that. Okay, B start to move at 8 meter per second, and then A will move at 2 meter per second. So A is slowing down, but B is picking up speed at this point. Okay, all right. So I'm going to show you what answer that we have obtained previously. We have already found out that this is BB is equal to 8 meter per second just now. And then A will slow down. It will be moving at 2 meter per second. B will be moving faster. And then it will be projected towards C in this case. Okay. All right. So that is how it actually looked like. So before the second collision, okay. So before the second collision, just let me show it to you here. So before the second collision, B would approach C now, of course. Okay, you can see that B approach C and coalesce, meaning that they join together. Okay, now don't forget that A is still in motion at this speed. Now these two will coalesce. Now bear in mind, just before B collide with C, its speed is 8 meter per second here. So when it collide, it coalesce. This whole thing here is known as object D here. So this object D will be moving with a certain velocity. Let's call that VD then, since they refer to object D then. All right, so if you are clear what we are looking at, now we're going to apply the conservations of momentum one more time. Now, when you look at these conditions, it looks a bit stressful, and then we have no idea what we are supposed to apply when we use conservation of momentum. So one of the easy way to look at this is since we are interested with the collisions between B and C, so why don't we just concentrate on uh, the system that consists of B and C only. Only look at B and C. Don't look at A anymore, even though A is also in the system itself. So we are only interested with B and C. So just focus at B and C. So divide and conquer. We can't multitask too much here. Right. So just focus on this. This will be our system. So therefore, by looking at this, using conservation of momentum again between B and C. All right, now between B and C. So therefore, total momentum before collide. Now we know that B is 2 kg, moving at 8 that we have already calculated. All right, okay, that's it. Plus the particle C, which is 3 kg at rest. Okay, that's how it looked like. And then when they collide, after they collide, okay, so after they collide, what happens is that they will join together. So when they join together, it means the total mass will be 2 plus 3. And then it will be moving as one object D in this case. So that is how it actually look like. In this case, the VD will be, in this case, for sure there's a 5 and then there's a 16. So therefore, the speed of D after collisions will be 16 divided by 5 here. So that will be 3.2 meter per second. All right. So I hope that is clear for this section here. Right. Okay. I'm going to move on to the last sections for this question shortly. All right. Last sections of question 8, section C here. Okay. Right. Now, we have seen the collisions between B and C. They coalesce, and then they will move as a one body object D. So now we need to show that the total loss of kinetic energy in the system, the whole system itself, due to the two collision is equal to 38.4 joule. So before we look into that, let's try to recap how the collision actually look like. So here I'll show you one more time. Okay, so A collide with B there, and then after the first collision, okay, so B will move there. Before the second collision, B will collide with C, and then after the second collision, BC will be moving uh, as one body object D here. Okay, so that's what we have. Okay, now we are good to go. We have already found that the speed of this object here, when it combine, is given by 3.2 meter per second. That's what we found out. And then A is still moving at so A, this is moving at this. A is still moving at 2 meter per second here. All right. So the loss in kinetic energy. So the first thing is it's always good to find out its change in kinetic energy. So change in kinetic energy. So the change in kinetic energy will be your final kinetic energy subtract off with your initial kinetic energy of the system itself. So the final kinetic energy, we can see that this is the final one. So it involves these two. So the final kinetic energy is given by the kinetic energy of particle sphere A. So that is 4 moving at 2 meter per second. And at the same time, we have a joint particle here, which has a mass of 5, moving at 3.2 square. All right, now that will be our final kinetic energy. Now we need to remove off the initial kinetic energy. The initial kinetic energy at the beginning. So let me show you one more time here. At the beginning there. So you can see that at the beginning, the only object that has kinetic energy is sphere A, moving at 6. So we're going to remove that off. 4 kg moving at 6 meter per second. So that's how it look like. So let's give that a try here. So we have a 2, we have a 8 here. Okay, so this one here we have let me see, we have 5 by 1.6 by 3.2 here, and then subtract off with this is 2, this is 36, 72 here. Okay, and then I'm going to do this slowly. So that will be an 8 by 3.2 minus 72 there, and then we have 8 by 4.2 here, of course. Okay, and then now that can be further factorized out again, because I don't use calculator most of the time, so I need to do a bit of algebra here. That will be a 9, so that will be by the 4.8 then. So that will be, oops, that will be 38, 38.4, 38.4 joule there. Now it is negative because the change in kinetic energy is negative. Therefore, we will say that the total loss of kinetic energy is equal to 38.4 joule there. So the negative actually show us that there is a loss of kinetic energy due to the collisions. So I hope this is clear. We're going to move on to the last questions today. All right, this is our last questions today. This is a question raised by one of my students. I found that there are lots of interesting discussions regarding this question here. So that's the reason why I bring up this question here. All right. Okay. Now, a particle of mass 18 kg is on a plane inclined at an angle 30 degree as shown. The particle is projected up the line of greatest slope of the plane with a speed of 20 meter per second as shown in the diagram. Now, given that the plane is smooth, okay, now use an energy methods to find the distance the particle move up the plane before coming to rest. Okay, before coming to rest here. All right, so let me see, is 18 kg is on the plane incline, so the particle is projected up with a speed of 20 meter per second here. All right, so that is what we are getting at, at this point of time. Okay, now anything else we need to know here? So we have to apply, use the energy method to find the distance the particle move up the plane before coming to instantaneous rest here. Okay, now before that there's an error. Just let me. All right, here I have already corrected the simulations here. You can see that there is uh, no continuous force that is pushing the object up anymore after the projection, and then the mechanics should look something like this. Let me show it to you here. All right, you can see that it move up Q, and then it will reach 0 meter per second due to the gravity. Eventually it's going to stop, not due to the smooth plane. If it is due to the smooth plane, it would actually continue forever. But due to the gravity itself, eventually it's going to stop there, right? So we're going to use the energy methods to find the distance the particle move up the plane before coming to instantaneously at rest. So to do that, now we're going to apply the work energy principle one more time. So we're going to use work energy principle here. All right, so I'm going to show you the first method here. We can also use the second method later on. All right, so using the first method, work energy principle, we know that work done must be equal to the change in kinetic energy, right? So the change in kinetic energy is actually given by half v squared minus u squared, the final speed subtract all with the initial speed. So in our case, we have half 18 here. The final speed is 0. The initial speed was 20, so it's 20 square here. And then that would be like a 9 negative here by 400. So that would actually yield negative uh, 3600 joule there. Right. So the change in kinetic energy is negative 3600 joule. Therefore, the work done. Okay. So we're going to look at the work done now. All right. Now, work done, which force actually contribute the work in this case? And you can see that the only force that is responsible for the work done in this case is the gravity. So we need to perform work to overcome the gravitational force here. Right? So that would be given by, don't forget that, sorry. So this one here is a theta. All right, now we have to resolve this weight component along the slope. So it must be along this slope here. That will be W sine theta. Yep, W sine theta multiplied by the distance that the object traveled just now. That'll be S. So the weight is 180 by sine 30, and then multiplied by the distance traveled. So from here, sine 30 is half, so you get 90 S here. All right, so I hope that is clear. Now, all we need to do is just equate this equation here. So therefore, we have 90 multiplied with the displacement is equal to 3600. Therefore, in this case, hold on. Oh yeah, I forgot that. Because the work done itself, the directions of the weight itself is in this direction, but the displacement is actually going upward. Okay, I just want to make it clear. The displacement is actually going upward. So therefore, we are doing work to overcome gravity. So because you're wasting your energy in this case. So therefore, you're losing energy due to gravity. So it's a negative. So there is a negative here. Yeah. So please pay attention to that. So from here, you will be able to get 40 meters. All right. So the distance travel up until it reach instantaneous rest is 40 meters, right? Using work energy principle here, right? Okay. Now, secondly, we can also solve this using kinematic and Newton's second law, right? So let me show it to you here. We can also use kinematic and Newton's second law. So second method is by using kinematic and Newton's second law. All right. So using kinematic here, we can find out its you can find out its acceleration in this case, right? Now by using all the forces that is acting on the object, so we're going to consider forces acting on the particle along the slope. So along the slope here, the only force that is acting on the particle along the slope is the weight itself. So therefore, by using Newton's second law, we will get okay. So in this case, because the motion is going up, so we are saying the acceleration is going up here. Uh, so therefore, is 0 subtract off with the W sine 30. Okay, that should yield acceleration, right? So from here we have 180 sine 30 degree. The mass is 18. Acceleration. Therefore, acceleration in this case will be, yeah, is quite direct. It's actually negative 10. So negative 10 sine 30 there. We know that sine 30 is half, so therefore this is negative 5 meter per second square. Okay, so it's decelerating, of course. Right. So from here, we can make use of the Suvet equation or the kinematic equation here. Right. We know that the final speed must be 0. Initial was 20. And then we have an acceleration of negative 5. The distance is the one that we are interested to obtain here. So from here, you get 10s is equal to 400. Therefore, this is equal to 40 meter. Right. Now, that's how we apply kinematic and Newton's second law to obtain the distance travel up the hill when it come to instantaneously at rest. All right. Now, I hope that is clear. We're going to look at the second part of this question, which is the last one shortly. All right. The second part of this question 9 here. Now, this time they change the scenario. Given instead that the plane is rough and the coefficient of friction between the particle and the plane is 0.25, we need to find the speed of the particle as it returns to its starting point. So what they mean is initially at the beginning, while the particle is being launched, the surface is already rough. So therefore, as the particle, as we know that the particle is moving upward, the frictional force will be acting in the opposite directions to the motion itself. Now, this is how it actually look like. So first of all, there are two stages here. The first one is going to move up. The frictional force is acting downward. Okay. Now observe closely. All right, you can see that. Secondly, it's going to slide down now. The frictional force would act in the opposite direction. All right. So I hope that is clear. All right. Now that is what it meant here. So we're going to use that all that information to help us to solve this. Okay. Now let me show you where this is. Let me show it up. Show up first. Okay. So up to here. Now I'm going to label this. Again, this is data 30 degree here. Okay. Now we're going to figure out because the surface is rough initially, therefore the distance travel would no longer be greater than 40. So I think that in my previous discussions, I assume that um, the surface is rough only after you reach the at the top there, which is the wrong which is a illogical assumption. So if this surface was rough initially, the frictional force would be acting on the object as it go up. So therefore, due to the friction, the distance travel would no longer be greater than 40 meter when it come to instantaneous rest. All right. So we're going to apply the same procedure again here. Okay. Now we can, yeah, you can use any methods here. Take for instant. In this case, I'm going to use kinematic. Kinematic first. Okay. All right. Kinematic and Newton's second law. Right. I'm going to solve it using this method first. Right. So first of all, my first intention is to figure out what is the distance travel before it reached instantaneous rest initially when it was projected at 20 meter per second there, right? So using this method, I'm going to consider forces acting on the particle, Right. Now here I will consider both the forces along the slope and perpendicular to the slope. So if I consider the force acting in the perpendicular directions, therefore I will be able to obtain the normal force, which is actually equal to 180 cosine 30. Okay, which is actually 90 sec 3 Newton here, right? So I hope that's clear. And then we know that frictional force is actually given by this, and then we knew that the coefficients of friction is given by 0.25 here. So I'm going to write that down, 0.25. The normal force is by this. Okay. So from here, I will be able to obtain, that will be 45, 22.5 sec 3 Newton. Okay, so that's the force that we have. Now, next we're going to consider the force acting along the slope. So along the slope now, we know that it must along the slope because the object is moving upward. Okay, initially, I think my arrow is wrongly drawn. So I'm actually considering the motion along the slope going up. So acceleration will be here. Okay. Now by applying Newton's second law, now I will have 0 minus frictional force, and then also the weight, which is sine theta, and then that must produce an acceleration. Okay, so I'm going to substitute all the value that I have. Frictional force is 22.5 sec 3. Okay, and then my weight is 180 sine 30. Yep, sine 30. In this case, my mass is 18 accelerations here. All right. So from here, I will get the 22.5 sec 3. That is typically a 90 equal to 18a there. Therefore, the acceleration, of course, this is more like a deceleration here. Okay, I'm going to bring up my calculator to help me with this computation here. Okay, hold on for a while. Let me see, what do I have here? I have, okay, so I have 22.5 multiplied by square root of 3. Okay, plus 90 there. Alright, so that is what I have. Okay, divide by 18 here. Now, therefore, the deceleration is negative 7.165 then, since this is not really my final answer, so I'll leave it as it is. So negative 7.165 meter per second. Alright, that's my acceleration. So by using the Suvet equation, v square equal to u square plus 2as. Alright, now I know that my final velocity is supposed to be 0, and then my initial was 20. My acceleration is negative 7.165 by the distance that I'm interested to find out. So that will be typically 400 divided by 2 by 7.165 here. Okay, let me take out my calculator one more time. So I have 200, basically 200 by t then. Okay, so therefore the distance that it managed to reach is 27.9 then, 0.9 meters to the nearest three significant figures. Right. So I hope that is clear. That is just the first part. Right. That's just the first part. Okay, that is just going up the slope. This is just going up the slope. Right. Okay, so I hope that is clear. Going up the slope, we managed to find out that the distance traveled now, due to the friction, is actually given by 27.9 meters now. Okay, we are good. Now we're going to look at when it slides down, to its original position. Yeah. when you slide down to the original positions there. Right, so I'm going to erase off this. Okay, all right. Okay, now I think I will still need to use this because I'm using um, kinematic equation and then considering the Newton's second law. All right, now you can see that from here, so it's going to slide down now. Okay, I'm going to pause there. So you can see that it's going to slide down now. It's going to slide down and then over the same distance here. It's just that the frictional force will be acting in the opposite directions there. Okay, we want to find out what is the speed here. Knowing that initially it was 0 here. Okay, what will be the speed here? All right. So again, we can apply the Soviet equation. So the only thing we have to figure out is now is actually accelerating downward. So the same thing here, we will have to consider. All right. So the same thing by considering the force acting perpendicular to the slope itself, we will be able to reach the conclusion about the normal force, which is 180. I'm going to write that down one more time. Okay, so from here, that is 90 Newton. Okay, and then I'm going to consider the forces down the slope now. Down the slope. Okay, so therefore, that will be weight sine theta, subtract off with the frictional force now, and then it would actually create an acceleration. So this is 180 sine 30 degree frictional force. All right, now frictional force we have already calculated that before this. It was 0.25 multiplied by 90 sub 3. Okay, 90 sub 3, and then that will be an acceleration. Okay, so from here we should be able to obtain the accelerations here. So this is 90 here, so we can actually divide 90, that will be a 5. So 5 minus 1.25 sub 3. Okay, so just let me get my calculator here. That will be 5 minus of 1.25 sub 3. Okay, that will give me an accelerations of 2.835 meter per second square. So just let me quickly check this if I got it correct. 5 here, 1.25, yes, correct. This is actually a 90, so 90 also divided by 5. Yep, correct. Okay, so there you go. That is the accelerations down the slope now. What we are interested to find out is the speed now, which is actually given by 0 square plus 2, the acceleration is this, and then the distance, the new distance is this. Therefore, in this case, we're going to take the square root directly. Okay, I'm going to calculate that directly so that we don't have to go through a hassle here to figure out what is the U. So I'm taking all the decimal number that I have. Of course, if you use the rounded off number, your final answer may be a bit different from mine here. So let me check. So this is U, that is 27. Is that correct? Let me see. The distance is 27.9. Yes, correct, 27.9. And then we have the accelerations there. Yes, correct. And the multiply by 2. Yep, correct. So now we have to take the square root of this, and then therefore I will be able to reach the speed when it return to its original position at 12.6 meter per second to nearest 3 significant figures there. All right. So I hope that is clear. Now, the only thing you have to remember, which have made a mistake on in my previous discussions, would be I forgot to consider that the terrain or the slope is rough now. So we will know that the distance travel up will be shorter than 40 meter, right? So I hope this has been a good exposure to all of you. These are very good questions here, right? So if you like what you are looking at, do subscribe and then click on the notifications bells to receive the latest video on mathematical topics. All right. Until then, I'll see you guys.